Welcome to This Explainer. Today, we're literally putting reality itself on trial. We're investigating a profound mystery right at the core of physics. Basically, is the universe secretly predetermined, running on some hidden clockwork, or is it fundamentally entirely unpredictable? I am so incredibly excited to guide you through this, because we're going to explore some of the absolute most mind-bending concepts ever conceived. Let's get right into it and uncover the truth step by step.
Think about it. Is the universe deciding what happens right this second, or was it all predetermined from the start? It kind of sounds like late-night dorm room philosophy, right? But this single question sparked arguably the greatest intellectual mystery of the 20th century. It completely pitted our comforting, everyday classical intuition against the absolute weirdness of quantum mechanics. So to understand how this massive debate was settled, we first need to lay down the rulebook of the universe.
Moving on to Section 1, the rules of reality. Let's establish the mathematical ground rules of our cosmic crime scene here. Okay, so the term Hilbert space. I know, it might sound incredibly intimidating at first glance, but I really want you to think of Hilbert space not as some daunting math term, but simply as the abstract game board where the quantum game is played. You know, just like chess happens on a grid of 64 squares, quantum reality unfolds in this complex, multidimensional mathematical landscape. And every single possible state of a quantum system is just represented as an arrow, a vector pointing somewhere in this space.
Now, to see why this is so revolutionary, we kind of have to compare it to our everyday world. In classical mechanics, the physics of baseballs and planets, we use what's called a phase space. In phase space, if you know a particle's position and momentum, you know its future with absolute certainty. It's perfectly deterministic. But quantum mechanics, it lives in Hilbert space, which is an entirely different mathematical arena. In Hilbert space, we aren't dealing with absolute certainties at all. We are purely dealing with probabilities.
So here's the quantum rulebook we're working with. We've got our state vectors, observables represented by mathematical operators, the famous Schrödinger equation governing how things evolve over time, and the Born rule for calculating the odds of what we might actually see. But the most shocking rule of the whole shebang is this: measurement causes the state vector to collapse. The rules of this game dictate that physical quantities, stuff like position or spin, are literally just mathematical probabilities floating in a haze of potential, up until the exact moment a measurement forces the system to pick a definitive outcome. It's wild.
That brings us to Section 2, Einstein's hidden variables. Now, what's truly fascinating is just how much these probabilistic rules bothered Albert Einstein. He was one of the founding fathers of quantum theory, but he absolutely hated the idea that reality was inherently random. In a famous 1935 paper, you've probably heard of it, the EPR paper, Einstein and his colleagues argued that quantum mechanics, with all its rolling of the dice, simply had to be incomplete. Their argument was essentially this: if you can predict a property without touching the system, that property must have been real all along. They firmly believed there must be hidden variables, secret gears and springs operating behind the scenes of the universe that the quantum math just couldn't see yet.
And Einstein's argument relied heavily on the principle of locality. This is the absolute bedrock of relativity. It insists that a particle can only be affected by what is immediately next to it, and absolutely nothing, no signal, no influence, can travel faster than the speed of light. Einstein firmly believed that spooky action at a distance was impossible. Therefore, particles must carry predetermined states with them from the moment they're created. It's kind of like a pair of gloves separated into two boxes. If you open one box and find a left glove, you instantly know the other is a right glove, right? Not because they magically communicated, but because they were always left and right to begin with.
All right, Section 3, Bell's brilliant game. For decades, this whole thing was just a philosophical debate. Einstein said the universe was predetermined and local. Quantum pioneers like Niels Bohr said it was fundamentally probabilistic. And there was literally no way to prove who was right, until a physicist named John Stuart Bell emerged as our quantum detective in 1964.
Bell brilliantly figured out a mathematical way to actually test whether reality uses Einstein's local hidden variables. He drew a line in the sand. He proved mathematically that no local hidden variable theory could ever fully replicate the predictions of quantum mechanics. It absolutely had to be one or the other.
But, that leaves us with a massive problem. How do you test reality? How do you go about proving the existence or non-existence of a hidden variable that, by definition, you can't even see? Well, the answer is a genius thought experiment that physicists later adapted into what's known as the CHSH inequality. We can visualize this test as a cooperative game played by Alice, Bob, and a referee named Victor. So Victor sends a random 0 or 1 to Alice and a random 0 or 1 to Bob. Alice and Bob are completely separated, meaning they cannot communicate at all once the game starts. They must each send a bit back to Victor, and they only win if their combined answers satisfy a very specific logic rule.
Now, here is the absolutely crucial point. If the universe uses classical local hidden variables, meaning Alice and Bob share some pre-agreed strategy or hidden instructions before the game starts, but can't talk during it, they can never, ever win this game more than 75% of the time. The math is absolute. 75% is the hard classical limit, no matter how clever their strategy is.
But here is where the magic happens. 0.85. If Alice and Bob share an entangled quantum state, meaning two particles fundamentally linked across space in that probabilistic Hilbert space we talked about earlier, their win probability magically jumps to roughly 85%. Quantum mechanics actively predicts they will beat the absolute limits of classical reality.
And this brilliantly illustrates how quantum physics permits a much higher mathematical correlation than classical local realism allows. In formal mathematical terms, the classical limit is bound at 2, but the quantum limit, which is known as the Tyrellson bound, reaches all the way up to 2 times the square root of 2. So suddenly, it was no longer a philosophical debate, it was a concrete mathematical test. If an experiment yielded a result greater than 2, Einstein's local hidden variables were completely dead in the water. Which brings us to Section 4, the ultimate verdict. Let's see how this builds from a brilliant mathematical theorem into rigorous, real-world experimental proof. Physicists spend decades turning Bell's math into a physical reality. Starting in the 1970s with John Clauser and advancing in the 1980s with Alan Aspect, physicists meticulously tested Bell's inequality using entangled photons. Over the years, culminating in a series of landmark tests in 2015, they methodically closed every single experimental loophole. Their dedication was so profound that Clauser, Aspect, and Anton Zeilinger were rightfully awarded the Nobel Prize in Physics in 2022. And let me tell you, closing those loopholes was no small feat. First, they had to tackle the locality loophole. This meant ensuring that the detectors were so far apart that no secret signal could possibly travel between them even at the speed of light, while the measurement was happening. Second, the detection loophole. This meant ensuring their equipment was efficient enough that no missing data was skewing the results. They rigorously ensured that nature simply couldn't cheat the test. And that brings us to the ultimate verdict. The experimental results consistently and definitively proved that physical systems obey quantum mechanics and they violate Bell inequalities. So what does that actually mean? It means Einstein's local hidden variables are completely, unequivocally ruled out. The universe is simply not playing by the classical rules we thought it was.
So where does that leave us? Well, it leaves us with some truly mind-bending interpretations of reality. Because Bell's theorem killed local realism, we basically have to give up either locality or realism. Maybe the Copenhagen interpretation is right, and realism is false, meaning particles literally don't have definite properties until we look at them. Or maybe the many worlds interpretation is true, and the universe splits into countless local branches every time a quantum event occurs. Or perhaps there are non-local hidden variables, meaning every particle in the universe instantaneously communicates with every other particle. Or honestly, most terrifyingly, superdeterminism, the idea that the universe is completely predetermined, including the so-called free will of the scientist choosing which measurements to make.
This quantum detective story has solved the initial mystery, only to reveal an even deeper one. The universe is demonstrably far stranger than our classical minds evolved to comprehend, which leaves us pondering one final, deeply unsettling question about the true nature of the reality we inhabit. If our universe isn't locally real, what else about reality are we taking for granted? Thanks so much for joining me on this explainer. Keep questioning everything.